All right, so we'll do a CIDR question, what I call a CIDR question. We're given an address. So we're given oops, hold on, I want to make sure I use the right one. So we're given that address, and it's a /22, meaning there's 22 bits in the network mask. And the question is, with that address and subnet mask, tell me what the subnet, the network is, the network address is, tell me what the mask is in decimal, and tell me what the broadcast address is for that address. So what's the very first thing I always do? I got my table. You don't have to do this, but this is what works for me. 2 to the 0, 1. You get it, you're bored. And then what's the other chart that I draw? What is that actually called? We call it the high order bits, because we're counting from the high end. Binary, it gets, the numbers are higher as you move from left to right, or I'm sorry, from right to left. And so the high order bits, 1, 0 equals 128 is 128. So this is, these spaces are 2 to the 0, 2 to the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th. 2 to the 7th. What is 2 to the 7th? 128. 2 to the 7th is 128. 2 to the 6th is 64. We add 128 plus 64 equals 192. 192 plus 2 to the 5th, 32, 224. Now we've added this spot, which is the 2 to the 0, 1, 2, 3, 4. 2 to the 4th is 16. 224 plus 16, 240. That's all we're doing, high order bits. That's going to be 8, so 248. Plus 4, 252. Plus 2, 254. And if they're all on, whoops. 255. Okay, I got my chart. We've got our problem. What's the next step? I heard someone say it, write out the mask. So I always like to write out the mask. It's a /22. What does a /22 look like? Well, it's 8 plus 8 more. 16, 17, 18, 19, 20, 21, 22, 23, 24. If you count up the ones, 8, 16, 17, 18, 19, 20, 21, 22. There's my mask. That's why the slash notation is so nice. It tells you exactly how many bits you have. So, which one is the octet of interest? Third octet. Why? Because this is where our split happens. We break right here. So this is where all the action's going to be. So it's this third octet that I care about. The fourth octet is going to be easy. It's either going to be 0 or 255. So either all bits off or all bits on are what we care about in these type of problems. So this is the quadrant, the third, octet that we care about. Now, I always use that phrase, magic number. What's my magic number in this case? 4. So where do we get 4? We have 2 bits here that are 0, and that's where it comes from. So that's 2 bits, 2 to the power of 2, right? That's this 2 matches that 2, equals 4. So our number is 4. What that number means is this octet is going to increment by 4s. So the networks are going to be 135. I'll write it out. 135.34.115. Oops. Sorry, that's the octet of interest. So the first one will be 0. Dot 0. So the first network is all the network bits in that octet are 0, which these are all zeros, and the network is always the host bits are all 0. So these are all zeros. So that's where that 0 and 0 comes from. The second network, these stay the same. Ditto, ditto, right? Because they're part of the network. We're not messing with these. These are the networks that you're given. You're only messing with the octet of interest. In here, the next network is going to be 4.0. So in decimal, that looks very challenging, or it doesn't look very clear, but let's look at this third octet. If the first network is 4 zeros, 6 zeros for the network portion, and we're saying it's the first network, so it's the all zeros network, plus the network always means the first, or all the host bits are 0. So all of that third, remember this is the third I'm playing around with, all that third octet is a 0. But we need the first network, and remember these first 2 bits are part of the host, right? So what's the very first network look like? Right? Sorry. Do you see how that these are the host bits? So the first network, this is a 1. If you look at that network section, isn't that how we always count in binary, right? The first digit is a 1, and then we go to a 1, 0, right, would be the next network. And the host bits are 0. Well, what is this? 2 to the 0, 2 to the first, 2 to the second. What's 2 to the second? 4. So this is showing it to you in binary. My little trick is to just figure out what the increment's going to be, and I can do it faster that way. But you can do it this way just fine. And look at, I did this switch, so I just answered the second network. What's the second network? Just like we always count in binary, it's going to be 0, 1. But this isn't in the 2 to the first place, right? It's actually in the 2 to the 0, 1, 2, 3. 2 to the third. What's 2 to the third? 8. Or you can just go 4, 8, 12, 16, da 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 da. So you're more than welcome to do that and write out each one of those networks. You might use the back of the sheet to do it. Or you can borrow my calculator. And you can just take the magic number, you take this number and divide it by the magic number. That should seem fairly simple, right? This is what the increments are going to be, 4, 8, 8. So if we want to find out what network this one's on, just divide it by 4. So 115 divided by 4 equals 28.75. So this address is on the 28th network, or subnet that we broke up, and it's around 3/4 of the way through that. We don't really care about the 0.75. We drop the 0.75, we drop the remainder, right? So it's 28. 28 times our magic number 4 equals 112. This network is 112. 135.34.112.0. And if we drew up 112 on here, and I'm not going to do it, if we drew it in binary, I'm betting dollars to donuts that the first two bits are going to be zeros, right? Because isn't the network mean all host bits are 0? So somehow in there is how we get to 112. Okay, and we won't bother drawing that. We want to get done on time tonight. So I've got the first question. It was net, mask, and decimal, and broadcast are the three questions. Here's our network. The broadcast is always 1 minus the next network. So that's why I always like to go one more past here. And our magic number is 4. 12 plus 4 is 16, right? Or 16. So that means the broadcast is 1 less than that. So the broadcast address for this network, I'll write it over here, is going to be 135.34.1 minus this. Exactly. I hear a lot of 115s out there. Beautiful. Dot 0? 255. Why is it 255? The broadcast, by definition, is all the host bits are on, or are ones. And I'll bet you, without even doing the math and looking at it, I'll bet you that in this case, these would both be on, right? Because these are part of the host portion of the address. These two would be on. And by the way, it has to be, at least this one has to be on. And you know how I know that? The only way you get an odd number in binary is 2 to the 0 being on. Right? I mean, look at it. Everything else is an even number. The only way you can ever get an odd number is if that first bit is on. It's the only odd number in binary. And then the last question, so this is the broadcast. The last question is always, or could be, what's the mask? I guess that's not the last question, that's the middle one. What is the mask? This should be the easiest one. If I was taking this, I'd write this one down first so I at least get some points. Just convert this, which is this, into our chart here, right? The mask, we drew it. Isn't this 255? So I'll write the mask right here. We've already drawn it out. Isn't all bits on 255? All bits on are 255. Not all the bits are on, so let's be careful here. We've got, this is when this chart comes in handy. 1, 2, 3, 4, 5, 6 bits are on. 1, 2, 3, 4, 5, 6, 252. No bits are on here, right? Dot 0. There's my mask, 255.255.252.0. Remember, I asked for it in decimal. Read the problems. I could ask for it in slash notation or decimal, either one. Because this is interchangeable with this, which is interchangeable with this. All those three mean the exact same thing. This is it in slash notation, this is it in binary, and this is it in decimal. They're all exactly the same.